Article 220.4 of the National Electrical Code, or NEC, addresses the calculation of branch circuit loads. Specifically, it focuses on motor loads that are not part of air conditioning or refrigeration systems. When dealing with such motor loads, the NEC mandates a specific calculation adjustment to ensure adequate circuit protection and prevent overloading. This adjustment involves multiplying the calculated load by a factor of 1.25. This factor accounts for the potential for motors to draw more current than their rated full load amperage, especially during starting or under heavy load conditions. In the scenario presented, the optional code calculation yields a load of 350 amps on a 120/208 volts, 3-phase, 4-wire meter center. Because this load isn't associated with air conditioning or refrigeration, Article 220.4 dictates that we must increase this calculated load by 25%. To determine the required ampacity for the protective device, such as a switch or circuit breaker, we perform the following calculation: 350 amps multiplied by 1.25, which equals 437.5 amps. The result of 437.5 amps represents the minimum ampacity that the protective device must be rated to handle. Now, we must assess whether a 400 amp switch or circuit breaker is sufficient to provide adequate protection for this load. Since 400 amps is less than the calculated 437.5 amps, a 400 amp device is not adequate. Using a device rated lower than the calculated load would violate the NEC and pose a significant risk of overheating, nuisance tripping, and potentially electrical fires. Therefore, it is essential to select a switch or circuit breaker with a rating that meets or exceeds the calculated ampacity of 437.5 amps. The next standard size circuit breaker or switch above 400 amps would typically be a 450 amp or 500 amp device, depending on the manufacturer's available sizes and the specific application. Always consult the NEC and relevant product standards to ensure that the selected overcurrent protection device is appropriate for the intended use and meets all applicable safety requirements. Choosing the correct size overcurrent protection device is critical for several reasons. Firstly, it protects the circuit conductors from overheating and potential damage due to excessive current flow. Secondly, it prevents damage to the connected equipment, such as motors, by interrupting the circuit in the event of an overload or short circuit. Thirdly, it helps to maintain the overall safety of the electrical system, reducing the risk of electrical fires and other hazards. In summary, when calculating the required ampacity for a switch or circuit breaker serving a motor load that is not part of an air conditioning or refrigeration system, always remember to multiply the calculated load by 1.25 as per NEC Article 220.4. In the case of a 350 amp calculated load, this results in a required ampacity of 437.5 amps, necessitating the use of a switch or circuit breaker rated higher than 400 amps. Always consult the NEC and qualified electrical professionals to ensure compliance with all applicable codes and standards. Let's further elaborate on the implications of NEC Article 220.4 and its application in various scenarios. This article is not just a simple multiplication rule, it is a critical safety measure designed to account for the specific characteristics of motor loads. Motors, unlike purely resistive loads such as heaters or incandescent lights, exhibit unique current draw patterns. Firstly, motors typically draw significantly higher current during startup than during normal operation. This inrush current, also known as locked rotor current, can be several times the motor's full load amperage. If the overcurrent protection device is not sized appropriately, this inrush current can cause nuisance tripping, interrupting power to the motor unnecessarily. Secondly, motors can experience overload conditions due to mechanical issues, excessive load, or voltage fluctuations. These overload conditions can cause the motor to draw more current than its rated full load amperage, potentially leading to overheating and damage if the overcurrent protection device is not properly sized. Article 220.4 addresses these factors by requiring the calculated load to be increased by 25%. This provides a safety margin to accommodate the motor's inrush current and potential overload conditions, ensuring that the overcurrent protection device will not trip unnecessarily while still providing adequate protection against excessive current flow. Now, let's consider some examples to illustrate the application of Article 220.4 in different scenarios. Example 1 involves a three-phase motor with a full load amperage of 50 amps, not part of an air conditioning or refrigeration system. According to Article 220.4, A. The calculated load for the branch circuit is 50 amps multiplied by 1.25, which equals 62.5 amps. Therefore, the overcurrent protection device must be rated at least 62.5 amps. A standard 70 amp circuit breaker would be suitable in this case, provided it meets all other applicable requirements of the NEC, such as interrupting rating in coordination with other protective devices. Example 2 is about a single-phase motor with a full load amperage of 10 amps, again, not part of an air conditioning or refrigeration system. Applying Article 220.4. A. The calculated load for the branch circuit is 10 amps multiplied by 1.25, which equals 12.5 amps. In this case, a 15 amp circuit breaker would typically be used, as it is the next standard size above 12.5 amps. It is important to note that Article 220.4 is not the only factor to consider when selecting the appropriate size overcurrent protection device for a motor circuit. Other relevant factors include the motor's starting method, the type of load it is driving, and the ambient temperature in which the equipment is operating. The NEC contains additional requirements and guidelines for motor circuit protection, which must be followed to ensure safety and compliance. In addition to Article 220.4. A. Other relevant articles in the NEC include Article 430, which covers motor circuits, motor circuit conductors, and motor overload protection, and Article 240, which covers overcurrent protection in general. These articles provide detailed requirements for selecting the appropriate size and type of overcurrent protection device for various motor applications. When selecting an overcurrent protection device for a motor circuit, it is also important to consider the device's interrupting rating. The interrupting rating is the maximum amount of fault current that the device can safely interrupt without being damaged. The interrupting rating must be sufficient to handle the available fault current at the point of installation. To determine the available fault current, a qualified electrical engineer or technician must perform a fault current study. This study takes into account the characteristics of the power source, the impedance of the circuit conductors, and the presence of any other equipment that may contribute to the fault current. Based on the results of the fault current study, an overcurrent protection device with an appropriate interrupting rating can be selected. Coordination is another important consideration when selecting overcurrent protection devices. Coordination refers to the selective tripping of overcurrent protection devices in a system such that only the device closest to the fault will trip, while upstream devices remain unaffected. This minimizes the disruption to the electrical system and allows for faster restoration of power. To achieve coordination, the time current characteristics of the overcurrent protection devices must be carefully selected and coordinated. This typically involves the use of fuses or circuit breakers with different time delay characteristics. The NEC provides guidance on coordination in Article 240.12 and other related section. In summary, the selection of the appropriate size and type of overcurrent protection device for a motor circuit is a complex process that requires careful consideration of various factors, including the motor's full load amperage, starting method, load characteristics, ambient temperature, interrupting rating, and coordination requirements. NEC Article 220.4 is a critical component of this process, ensuring that the calculated load is increased by 25% to account for the unique characteristics of motor loads. However, it is just one piece of the puzzle, and other relevant articles in the NEC must also be followed to ensure safety and compliance. Always consult the NEC and qualified electrical professionals to ensure that the selected overcurrent protection device is appropriate for the intended use and meets all applicable safety requirements. Let's delve deeper into the practical implications of ensuring proper overcurrent protection in electrical systems, particularly concerning motor loads. We've established that NEC Article 220.4 is paramount when dealing with motor circuits not associated with air conditioning or refrigeration, necessitating a 1.25 multiplier on the calculated load. However, the real-world application of this principle extends beyond simple calculations. It involves a thorough understanding of the electrical system's characteristics and potential failure modes. Firstly, consider the scenario of a manufacturing plant utilizing numerous motors for various industrial processes. Each motor, depending on its horsepower and application, will have a specific full load amperage, or FLA, rating. When designing the electrical distribution system for this plant, engineers must meticulously calculate the total load imposed by these motors, accounting for the 1.25 multiplier stipulated by Article 220.4 for each applicable motor. This calculation forms the basis for selecting the appropriate size of conductors, overcurrent protection devices, and transformers to ensure the system can safely handle the anticipated load. Secondly, let's examine the impact of motor starting methods on overcurrent protection. Motors can be started using various methods, such as across-the-line starting, reduced voltage starting, or variable frequency drives. Each method has a different impact on the magnitude and duration of the inrush current. Cross-the-line starting, for example, typically results in a very high inrush current that can be several times the motor's FLA. Reduced voltage starting methods, such as auto-transformers or part-winding starters, reduce the inrush current but may also reduce the motor's starting torque. Variable frequency drives, or VFDs, offer the most control over motor starting and can minimize the inrush current while providing smooth acceleration. The choice of motor starting method will directly influence the selection of overcurrent protection devices. For motors started across the line, time delay fuses or inverse time circuit breakers may be necessary to prevent nuisance tripping due to the high inrush current. Reduced voltage starting methods may allow for the use of smaller overcurrent protection devices, while VFD typically include built-in overload protection that can eliminate the need for separate overload relays. Thirdly, consider the effects of ambient temperature on overcurrent protection devices. Overcurrent protection devices, such as fuses and circuit breakers, are temperature-sensitive devices. Their current carrying capacity is affected by the ambient temperature in which they are operating. At higher ambient temperatures, the current carrying capacity of these devices decreases, while at lower ambient temperatures, it increases. The NEC requires that overcurrent protection devices be derated for ambient temperatures above 30 degrees Celsius, or 86 degrees Fahrenheit. This derating ensures that the devices will provide adequate protection even at elevated temperatures. The derating factors for different types of overcurrent protection device are specified in the NEC tables. In addition to ambient temperature, the altitude at which the equipment is operating can also affect the current carrying capacity of overcurrent protection devices. At higher altitudes, the air is thinner, which reduces the cooling effect of convection. This can lead to increased temperatures and reduced current carrying capacity. The NEC does not specifically address altitude derating for overcurrent protection devices, but manufacturers typically provide guidance on this topic. Fourthly, let's address the importance of coordination between overcurrent protection devices. As mentioned earlier, coordination refers to the selective tripping of overcurrent protection devices in a system such that only the device closest to the fault will trip, while upstream devices remain unaffected. This minimizes the disruption to the electrical system and allows for faster restoration of power. Achieving coordination requires careful selection and coordination of the time current characteristics of the overcurrent protection devices. This typically involves the use of fuses or circuit breakers with different time delay characteristics. For example, a fuse with a longer time delay may be used to protect a feeder circuit, while a circuit breaker with a shorter time delay may be used to protect a branch circuit. The time current curves of the devices must be coordinated to ensure that the branch circuit breaker will trip before the feeder fuse in the event of a fault on the branch circuit. Fifthly, consider the role of ground fault protection in motor circuits. Ground faults are a common type of electrical fault that can occur when a conductor comes into contact with ground. Ground faults can cause significant damage to equipment and pose a serious safety hazard. Ground fault protection is designed to detect and interrupt ground faults, preventing damage and reducing the risk of electrical shock. The NEC requires ground fault protection for certain types of motor circuits, such as those serving fire pumps or emergency systems. Ground fault protection is typically provided by a ground fault circuit interrupter, or GFCI, or a ground fault relay. A GFCI is a device that monitors the current flowing through a circuit and interrupts the circuit if it detects a difference between the current flowing in the hot conductor and the current flowing in the neutral conductor. This difference indicates that current is leaking to ground, which is a sign of a ground fault. A ground fault relay is a device that monitors the current flowing in a ground conductor and trips a circuit breaker if it detects excessive ground current. Ground fault relays are typically used in larger electrical systems where GFCI protection is not practical. In conclusion, ensuring proper overcurrent protection in electrical systems, particularly concerning motor loads, is a multifaceted task that requires a thorough understanding of the NEC electrical system characteristics and potential failure modes. NEC Article 220.4 is a critical component of this process, but it is just one piece of the puzzle. Other important considerations include motor starting methods, ambient temperature, coordination, and ground fault protection. By carefully considering all of these factors, engineers and electricians can design and install electrical systems that are safe, reliable, and compliant with the NEC. Furthermore, remember that electrical codes and standards are constantly evolving to address new technologies and emerging safety concerns. It's crucial to stay updated on the latest revisions of the NEC and other relevant standards to ensure that your electrical work is always in compliance. Continuing education courses, industry publications, and professional organizations are valuable resources for staying informed about the latest developments in the electrical field. In addition to adhering to codes and standards, it's also essential to follow best practices for electrical safety. This includes using proper personal protective equipment such as gloves, safety glasses, and insulated tools, and following lockout/tagout procedures when working on energized equipment. Never work on electrical equipment while it is energized unless you are specifically trained and authorized to do so. Always double-check your work to ensure that all connections are tight and that all components are properly installed. By following these best practices, you can minimize the risk of electrical accidents and injuries. Finally, remember that electrical work is not a do-it-yourself project. It requires specialized knowledge, skills, and equipment. If you are not a qualified electrician, do not attempt to perform electrical work yourself. Hire a licensed and insured electrician to handle any electrical repairs or installations. A qualified electrician will have the training and experience necessary to perform the work safely and correctly, ensuring that your electrical system is reliable and compliant with all applicable codes and standards. By taking these precautions, you can protect yourself, your family, and your property from the hazards of electricity. The principles discussed extend beyond residential or commercial settings and apply equally to industrial applications, where motor loads are often more significant and complex. In these settings, proper overcurrent protection is even more critical due to the potential for greater disruption and financial losses in the event of equipment failure or downtime. For instance, in a large manufacturing facility, a single motor failure can halt production lines, resulting in significant financial losses. Therefore, ensuring adequate overcurrent protection for these motors is not only a matter of safety but also a matter of business continuity. In addition to the factors already discussed, industrial applications often require more sophisticated overcurrent protection schemes such as differential protection or motor protection relays. Differential protection is a technique that compares the current entering and leaving a piece of equipment such as a transformer or a motor. If there is a significant difference between the two currents, it indicates that there is a fault within the equipment, and the protection system will trip the circuit breaker to isolate the faulty equipment. Motor protection relays are specialized devices that provide comprehensive protection for motors against a variety of fault conditions such as overloads, short circuits, ground faults, phase imbalances, and undervoltage. These relays typically include advanced features such as thermal modeling, which simulates the temperature of the motor windings to provide early warning of potential overheating. They may also include communication capabilities that allow them to be integrated into a plant-wide monitoring and control system. The selection and application of these advanced overcurrent protection schemes require a thorough understanding of the electrical system and the characteristics of the equipment being protected. It is essential to consult with qualified electrical engineers and protection specialists to ensure that the protection system is properly designed and coordinated. Furthermore, regular testing and maintenance of overcurrent protection devices are crucial to ensure that they will function correctly in the event of a fault. Testing should be performed according to the manufacturer's recommendations and applicable standards. Maintenance should include visual inspections, cleaning, and lubrication of moving parts. Any damaged or worn component should be replaced promptly. In conclusion, ensuring proper overcurrent protection in electrical systems is a complex and multifaceted task that requires a thorough understanding of the NEC electrical system characteristics, potential failure modes, and advanced protection schemes. It is essential to follow best practices for electrical safety and to consult with qualified electrical professionals to ensure that the protection system is properly designed, installed, and maintained. By taking these precautions, you can minimize the risk of electrical accidents, protect equipment from damage, and ensure the reliable operation of electrical systems.